A geometric algebra is a Clifford algebra of a vector space over the field of real numbers endowed with a quadratic form. The term is also sometimes used as a collective term for the approach to classical, computational and relativistic geometry that applies these algebras. The Clifford multiplication that defines the GAR as a unital ring is called the geometric product. Taking the geometric product among vectors can yield bivectors, trivectors, or general n-vectors. The addition operation combines these into general multivectors, which are the elements of the ring. This includes, among other possibilities, a well-defined formal sum of a scalar and a vector. Geometric algebra is distinguished from Clifford algebra in general by its restriction to real numbers and its emphasis on its geometric interpretation and physical applications. Specific examples of geometric algebras applied in physics include the algebra of physical space, the space-time algebra, and the conformal geometric algebra. Geometric calculus, an extension of GAR that incorporates differentiation and integration, can be used to formulate other theories such as complex analysis, differential geometry, e.g., by using the Clifford algebra instead of differential forms. Geometric algebra has been advocated, most notably by David Hastings and Chris Doran, as the preferred mathematical framework for physics. Proponents claim that it provides compact and intuitive descriptions in many areas including classical and quantum mechanics, electromagnetic theory and relativity. GAR has also found use as a computational tool in computer graphics and robotics. The geometric product was first briefly mentioned by Hermann Grassmann, who was chiefly interested in developing the closely related exterior algebra, which is the geometric algebra of the trivial quadratic form. In 1878, William Kingdon Clifford greatly expanded on Grassmann's work to form what are now usually called Clifford algebras in his honor. For several decades, geometric algebras went somewhat ignored, greatly eclipsed by the vector calculus then newly developed to describe electromagnetism. The term geometric algebra was repopularized by Hastings in the 1960s, who recognized its importance to relativistic physics. Definition and notation. Given a finite-dimensional real quadratic space V equals Rn with a quadratic form G, VR, the geometric algebra for this quadratic space is the Clifford algebra C. The algebra product is called the geometric product. It is standard to denote the geometric product by juxtaposition. The above definition of the geometric algebra is abstract, so we summarize the properties of the geometric product by the following set of axioms. The geometric product has the following properties: where A, B and C are any elements of the algebra, and where A, B and C are any elements of the algebra, where A is a vector. Note that in the final property above, the square need not be non-negative if G is not positive definite. An important property of the geometric product is the existence of elements with multiplicative inverse, also known as units. If A2 0 for some vector A, then a -1 exists and is equal to A2. Not every non-zero element of the algebra is necessarily a unit. For example, if U is a vector in V such that U2 equals 1, the elements 1 plus or minus U are zero divisors and thus have no inverse. Equals 1 minus U equals 1 minus 1 equals 0. There may also exist non-trivial idempotent elements such as 2. Inner and outer product of vectors for vectors A and B. We may write the geometric product of any two vectors A and B as the sum of a symmetric product and an antisymmetric product. Thus we can define the inner product of vectors as the symmetric product, which is a real number because it is a sum of squares. Conversely, G is completely determined by the algebra. The antisymmetric part is the outer product of the two vectors. The inner and outer products are associated with familiar concepts from standard vector algebra. Pictorially, A and B are parallel if their geometric product is equal to their inner product, whereas A and B are perpendicular if their geometric product is equal to their outer product. In a geometric algebra for which the square of any non-zero vector is positive, the inner product of two vectors can be identified with the dot product of standard vector algebra. The outer product of two vectors can be identified with the signed area enclosed by a parallelogram, the sides of which are the vectors. The cross product of two vectors in 3 dimensions with positive definite quadratic form is closely related to their outer product. Most instances of geometric algebras of interest have a non-degenerate quadratic form. If the quadratic form is fully degenerate, the inner product of any two vectors is always 0, and the geometric algebra is then simply an exterior algebra. Unless otherwise stated, this article will treat only non-degenerate geometric algebras. The outer product is naturally extended as a completely antisymmetric, multilinear operator between any number of vectors, where the sum is over all permutations of the indices, with the sign of the permutation, blades, grading, and canonical basis a multivector that is the outer product of our independent vectors. We denote this algebra, for example, models 3D Euclidean space, relativistic spacetime, and a 3D conformal geometric algebra. The set of all possible products of n orthogonal basis vectors with indices in increasing order, including 1 as the empty product, forms a basis for the entire geometric algebra. For example, the following is a basis for the geometric algebra. A basis formed this way is called a canonical basis for the geometric algebra, and any other orthogonal basis for V will produce another canonical basis. Each canonical basis consists of 2n elements. Every multivector of the geometric algebra can be expressed as a linear combination of the canonical basis elements. If the canonical basis elements are by is, with S being an index set, then the geometric product of any two multivectors is grade projection. Using a canonical basis, a graded vector space structure can be established. Elements of the geometric algebra that are simply scalar multiples of 1 are grade 0 blades and are called scalars. Non-zero multivectors that are in the span of a grade 1 blades and are the ordinary vectors. Multivectors in the span of a grade 2 blades and are the bivectors. This terminology continues through to the last grade of n vectors. Alternatively, grade n blades are called pseudoscalars, grade n-1 blades pseudovectors, etc. Many of the elements of the algebra are not graded by this scheme since they are sums of elements of differing grade. Such elements are said to be of mixed grade. The grading of multivectors is independent of the orthogonal basis chosen originally. A multivector may be decomposed with the grade projection operator, which outputs the grade R portion of A. As a result, as an example, the geometric product of two vectors since n and for I other than 0 and 2. The decomposition of a multivector may also be split into those components that are even and those that are odd. This makes the algebra a Z2-graded algebra or superalgebra with the geometric product. Since the geometric product of two even multivectors is an even multivector, they define an even subalgebra. The even subalgebra of an n-dimensional geometric algebra is isomorphic to a full geometric algebra of dimensions. Examples include an k-dimensional subspace W of V is represented by taking an orthogonal basis and using the geometric product to form the blade D equals B1, B2, Bk. There are multiple blades representing W. All those representing W are scalar multiples of D. These blades can be separated into two sets: positive multiples of D and negative multiples of D. The positive multiples of D are said to have the same orientation as D, and the negative multiples the opposite orientation. Blades are important since geometric operations such as projections, rotations and reflections depend on the factorability via the outer product that n blades provide, but that grade n multivectors do not when n4. Unit pseudoscalars. Unit pseudoscalars are blades that play important roles in GAR. A unit pseudoscalar for a non-degenerate subspace W of V is a blade that is the product of the members of an orthonormal basis for W. It can be shown that if I and I are both unit pseudoscalars for W, then I equals plus or minus I, and I2 equals plus or minus 1. Suppose the geometric algebra with the familiar positive definite inner products on Rn is formed. Given a plane of Rn, one can find an orthonormal basis B1, B2, spanning the plane, and thus find a unit pseudoscalar I equals B1, B2 representing this plane. The geometric product of any two vectors in the span of B1 and B2 lies in, that is, it is the sum of a zero vector and a two vector. By the properties of the geometric product, I2 equals B1 B2 B1 B2 equals minus B1 B2 B2 B1 equals minus 1. The resemblance to the imaginary unit is not accidental. The subspaces are algebra isomorphic to the complex numbers. In this way, a copy of the complex numbers is embedded in the geometric algebra for each two-dimensional subspace of E on which the quadratic form is definite. It is sometimes possible to identify the presence of an imaginary unit in a physical equation. Such units arise from one of the many quantities in the real algebra that square to minus 1, and these have geometric significance because of the properties of the algebra and the interaction of its various subspaces. An exceptional case occurs. Given a canonical basis built from orthonormalize from V, the set of all two vectors is generated by labeling these I, J and K. The subspace generated by zero vectors and two vectors is exactly this set is seen to be a subalgebra, and furthermore is our algebra isomorphic to the quaternions. In other important algebraic system, dual basis let be a basis of V, i.e., a set of n linearly independent vectors that span the n-dimensional vector space V. The basis that is dual to is the set of elements of the dual vector space V that forms a bi-orthogonal system with this basis, thus being the elements denoted satisfying where delta is the Kronecker delta. Given a non-degenerate quadratic form on V, V becomes naturally identified with V, and the dual basis may be regarded as elements of V, but are not in general the same set as the original basis. Given further a GAR of V, let be the pseudoscalar formed from the bases. The dual basis vectors may be constructed as where the denotes that the ith basis vector is omitted from the product. Extensions of the inner and outer products. It is common practice to extend the outer product on vectors to the entire algebra. This may be done through the use of the grade projection operator. This generalization is consistent with the above definition involving antisymmetrization. Another generalization related to the outer product is the commutative product. The regressive product is the dual of the outer product with the unit pseudoscalar of the algebra, and for multivector, the inner products on vectors can also be generalized, but in more than one non-equivalent way. The paper gives a full treatment of several different inner products developed for geometric algebras and their interrelationships, and the notation is taken from there. Many authors use the same symbol as for the inner product of vectors for their chosen extension. No consistent notation has emerged. Among these several different generalizations of the inner products on vectors are dot product makes an argument for the use of contractions in preference to Hestens's inner product. They are algebraically more regular and have cleaner geometric interpretations. A number of identities incorporating the contractions are valid without restriction of their inputs. Benefits of using the left contraction as an extension of the inner products on vectors include that the identity is extended to for any vector in multivector B, and that the projection operation is extended to for any blades A and B. Terminology specific to geometric algebra. Some terms are used in geometric algebra with a meaning that differs from the use of those terms in other fields of mathematics. Some of these are listed here. Vector ingar. This refers specifically to an element of the one-vector subspace unless otherwise clear from the context, despite the entire algebra forming a vector space. Grading ingar. This refers to a grading as an algebra under the outer product, and not under the geometric product. Outer product ingar. This refers to what is generally called the exterior product. It is not the outer product of linear algebra. Inner product ingar. This generally refers to a scalar products on the vector subspace and may include any chosen extension of this product to the entire algebra. It is not specifically the inner product on a normed vector space. Versa ingar. This refers to an object that can be constructed as the geometric product of any number of non-null vectors. The term otherwise may refer to a unit quaternion, analogous to a rotor ingar. Automorphism. This term is used only ingar, and refers to a linear map on the vector subspace, extended to apply to the entire algebra by defining it as preserving the outer product.